So section 6.3, we're learning one new set of identities. Okay, one new set of identities, and they're called the composite identities. Okay, what does composite mean in general? Finish your text and get out your earbuds and all that good stuff. If something is composite, it kind of means composed of, right? So like a composite piece of wood would be something that's composed of materials. That's what it means of it. It's made up of two angles. That's what that means. A composite identity is made up of two angles. So it's going to look something like this. It's going to look like cosine of x plus y, or you might see it as sine of a plus b, or it might be tangent of alpha plus beta. Okay, it could even be minus. It could be plus or minus. We call x plus y, or a plus or minus b, or alpha plus beta. We call those composite angles. Composite angles. Now, what these identities that we're going to learn allow us to do is it allows us to break down the composite angle and represent the function in terms of the original angles, the smaller angles. Okay. Now, my question to you is: do you think cosine of x plus y is as simply easy as distributing the cosine inside and calling it cosine x plus cosine y? You think it's that easy? It's not. Okay. Because we're not distributing a number into parentheses. It's not multiplication. This is a function. It's cosine of x plus y. So just like we couldn't distribute the natural log of a plus b, that does not work. We can't do the same thing with cosine. You can't distribute a function inside of itself. Okay. So we are going to learn a way to expand it out. And here it is for cosine. Right? So you got to memorize this. Memorize. Cosine of x plus y is cosine x cosine y minus sine x sine y. And cosine of x minus y is cosine x cosine y plus sine x sine y. Now, what are some observations one can make about these two identities that might help you remember them? Yeah, that's the first thing that might jump out at you. The sign is opposite, right? It's the opposite sign. So if you're adding angles on the inside, you're going to be subtracting the two functions. And if it's subtracted on the inside, you're going to be adding on the outside. So that's a good observation. What else? Yeah, so you're taking the cosine and sine of each angle, right? And if you notice, this is easy. The cosines go first, right? The cosines go first, and then the sines go second. So I always say that cosine is a me monster. You ever known a me monster? They're all about themselves. They're like, me first, mine, me, mine, me. So here's how I always remember it. Because the function is a cosine identity, right? It's cosine of x plus y, cosine of x minus y. Cosine wants to go first. He's like, this is my identity, boy. I'm going first. My identity, I'm first. So cosine, cosine. And then sine is like, man, we're going to get to the stoplight at the exact same time, dude. We're both going to have to wait there. There's no rush. I don't mind going second, said sine. So sine is selfless and cosine is selfish. Got it? Cosine is selfish. Sine is second. That's kind of, yeah, you can say that too. So sine is second if you like the S sound, or you could say sine is selfless is what I've said before. And cosine is selfish. It's me. Now, you can also think about there is a price for being selfish, right? The price for being selfish is the sign changes, right? Okay, you can go first, but there's a consequence. The sign's going to change. So cosine, sine. Cosine of x plus y, cosine. Me, right? And then you. Me first, and then you. So me, you. Me, you. Cosine is selfish. Got it? Y'all can remember that. Here's how you can write both of them in one identity if you prefer to memorize it this way. Cosine of x plus or minus y is me, cosine, and then it's minus plus. That means that you change the sign, right? When it's flipped like that, that means you change the sign. A sine x, sine of y. All right, change the sign. Cosine goes first. Let's try it out. Let's see what we could do to help us remember this. Let's use it. Find the simplified exact value of cosine of 15 degrees by finding two angles from the unit circle that either add or subtract to give you 15. Okay, first of all, 15 is not one of the angles on the unit circle that we memorized, is it? It's a very shallow angle right here, 15. Okay, so we don't have it memorized by heart. There's Ryan, I guess. We don't have it memorized by heart, but here's where the composite identity comes in. If I can find two angles from the unit circle that I did memorize, and they add up or subtract to give me 15, then I can use the composite identity to find the exact value using using the values that I already have memorized. So help me out here. 15 degrees is equal to what on the unit circle? Well, yes, it is pi twelfths. Yeah, it is pi twelfths. But what are two angles from the unit circle that add or subtract to give me 15? 30 and 45. What would I have to do with them? I would have to subtract them. So 45 minus 30 is 15, right? 45 and 30 are on the unit circle. Are those the only ones? No, you could do 60 minus 45, right? There's a lot of them. 60 minus 45 will give you 15 as well. We only need one pair. So let's use the 45 and 30. So here's what we're going to write. Come over here on the left side now. Say cosine of 15 degrees is equal to cosine of 45 degrees minus 30 degrees. And now I can use the identity to expand it out. Is it just cosine of 45 minus cosine of 30? No way. It's the identity. It's cosine, cosine, me. So it's cosine of the first times cosine of the second. And because it's a minus sign inside, it becomes a plus sign on the outside. Change the sign. And then it's selfless sign going second. Sine of 45, sine of 30. That's using the identity. All right, now I can just evaluate it from the unit circle. What's cosine of 45 from the unit circle? No. Well, it's the same as cosine of pi fourth. I want the ratio there. Cosine of 45 degrees is the same as cosine of pi fourth. Cosine of 45 degrees is not pi fourths, okay? 45 degrees is pi fourths. What's the ratio at 45 degrees for cosine? Positive square root of 2 over 2. Got it? All right, what's the cosine of 30 degrees? Don't say pi 6. It's the cosine of pi 6, which is square root of 3 over 2. Yeah. Plus, what's the sine of 45 degrees? Also square root of 2 over 2. And what's the sine of 30 degrees? 1/2. Okay, there you go. Now I can multiply straight across. What's the square root of 2 times the square root of 3? It's the square root of 6 over 2 times 2 is 4. Plus the square root of 2 times 1 is the square root of 2 over 4. I got a common denominator, so I can add them together. Square root of 6 plus the square root of 2 all over 4. And there's the simplified exact answer. It's an irrational number because the square root of 6 and the square root of 2 are both irrational. Now, let's see if that's true. Let's go to the calculator if you want to queue up Minnesota. Come on, Minnesota. I got like 152 browsers open for Minnesota. You think that's the right answer? Does it feel like witchcraft or does it feel like it should work? You think so? Let's try it. If the calculator verifies it for us, does that prove that it works? No. It only verifies that it works for this angle, right? Remember, no amount of verification constitutes a proof. Now, you'd probably trust your calculator that it's going to work for other values, right? So what mode should I be in here? I should be in degree mode. Let's go to degree mode. And now I'll just type in cosine of 15. Should it be closer to 1 or closer to 0? No. It should be closer to 1 because 15 degrees is a shallow angle. This is 1, 0, and we've barely rotated up a little bit. So it should be closer to 1. Yeah, there it is. See, we're thinking all the time, aren't we? It's 0.9659. Now, let's type in the expression we got. Alpha x, we go the square root of 6 plus the square root of 2 all over 4. And You think it's going to be the same number? And I hope so. Yeah, it is the same number. Very good. So it works. At least it works for 15 degrees, right? Do you want to do it using 60 and 45, or you think that it's unnecessary? Do you think it'll work with 60 and 45? Yeah, it should work. Okay, so here's what's cool now. We have expanded our repertoire of the unit circle. Not only can I find the exact value of all the units, all the angles on the unit circle that I've already memorized, but now, because I can write angles in increments of 15 degrees by doing subtraction or addition, I can now find the simplified exact value of all the angles around the unit circle that are multiples of 15 degrees or multiples of pi twelfths. Okay? Anything that's a multiple of 15 degrees or anything that's something pi twelfths, you can write an exact answer for. Okay? So that's what it says right here. As long as it's a multiple of 15 degrees or pi twelfths, we can find the exact answer for it. All right, let me show you what I mean. Let's do it down here. Find the simplified exact value of 7 pi twelfths by finding two angles from the unit circle that either add or subtract to give you 7 pi twelfths. Okay, so let's focus on 7 pi twelfths. First of all, where does 7 pi twelfths live? Third? It should be in the second quadrant, yeah. And the cosine there is what? Positive or negative? Negative. So I know cosine of 7 pi twelfths is some negative number. Now, 7 pi twelfths is not one that we memorized, is it? But because it's a multiple of pi twelfths, which is 15 degrees, we're going to be able to find two angles that add or subtract to give it to us. So how can we find those two angles? No, because 7 is less than 12, so it's less than pi. This is 12 pi twelfths. Remember, this is pi? So this is 7 pi twelfths. Mm-hmm. How are we going to do that? How can we find two angles that add or subtract? Do you want to convert this to degrees? Is it easier to find two angles when it's in degree form like we did up here? It is, but I don't want you to have to convert it to degrees, so let's not do that. Okay, here's the easy way to find two angles. Take whatever is in the numerator, which is the 7, and try to write it as the sum of two numbers that share factors of 12. What are the factors of 12? 1 and 12, 2 and 6, 3 and 4. Okay? If you can write 7 as the sum of any two of those, you'll have it. Now, could I use 6 pi and 1 pi? I know 6 pi twelfths would simplify down to pi halves, but do I know what 1 pi twelfths is? No, I don't. So I can't use the 6 and 1 combo. What about the 3 and 4 combo? Would that work? Yeah, I could use the 3 and 4 combo. So 3 pi plus 4 pi. Here's why it works. If you simplify it down, you get 3 pi twelfths plus 4 pi twelfths, and those will simplify down because there's a common factor with 12 to pi fourths plus pi thirds. And there you go. We found two numbers that add up to give us 7 pi twelfths. So let's come over here to the right-hand side now, and we'll say cosine of 7 pi twelfths is equal to cosine of the two angles, pi fourths plus pi thirds. And now we'll use the identity, which is cosine, so he's selfish, me, cosine, 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 cosine of the first times cosine of the second. And what becomes of the sign? It becomes minus now, and then it's sine of the first, sine of the second. Sine's like, what is the big deal? Oh my gosh, cosine. Chill out, buddy. All right, now we just evaluated from the unit circle. What's cosine of pi fourths? Square root of 2 over 2. What's cosine of pi thirds? 1/2. Minus, what's sine of pi fourths? Square root of 2 over 2. What's sine of pi thirds? Square root of 3 over 2. So that becomes square root of 2 over 4 minus square root of 6 over 4. And if we put it in one term, it becomes square root of 2 minus the square root of 6 over 4. Now, notice we get the same numbers that we did in the previous one. The square root of 2 and the square root of 6 reappear. And you should expect that because we're pulling values from the unit circle and those are the numbers that appear when you multiply the numerators, okay? The only difference is it's in a different combination, isn't it? Instead of adding them together, like we did up here, we're subtracting one from the other. So let's see if it's right. I got to go back to radian mode now. So I got to go back to mode, go back to radian mode, and let's type in cosine of 7 pi divided by 12. It should be a negative number, negative 2.58. Okay, and let's type in what we found here, alpha x. That's the square root of 2 minus the square root of 6 all over 4. You think it's going to be the same number? It sure is. It sure is. So there you go. Proof that, at least for the angles that we've tried out, if we trust our calculator on the others, it should work. We can now write the exact value of any angle that is a multiple of pi 12ths, or 15 degrees. Okay? So the unit circle's power is now expanding. Would you agree? Good. Good. Sweet. All right, so that's it for cosine. Any questions on the cosine identities? All right. Let's do one more proof here, and then we'll be done. Using the cofunction identity, or yeah, derive an identity for sine of x minus y. Actually, instead of doing that, let's do something else. Let's prove this first. I'm going to change the instructions here. Okay, I want to prove this identity. Let's draw a line down the middle. I'm changing the instructions. We'll circle back to example 3 tomorrow and derive an identity. But right now, I just want to prove it. Okay, so let's start on the right-hand side. Using the identity, I get cosine of the first, cosine of the second, plus sine of the first, sine of the second. Yes, yes? That's using the identity. We couldn't prove the cofunction identities until we had the composite identities. Now, what's cosine of pi halves? So I get 0 times cosine of x plus, what's sine of pi halves? 1 times sine of x. What's 0 times anything? 0. So I get 0 plus sine of x, and I get what? Sine of x. We just proved the identity. Congratulations. So now we know that the cofunction identity for sine and cosine, they work for all values in the domain. Okay, so we'll stop there. I'll circle back and do example 3 the right way. It says to use it to derive an identity for sine of x plus y. Any questions so far today? That's it. All right. See y'all tomorrow.